Alright, we're going to do the next section, which is about interference. Now we've covered some about interference, but now we're going to do it just some more. We've done the double slit interference, we've done the wave interferences. This is some more types of interference. And we're going to start talking about this kind of interference. We're going to start with talking about going from the idea of we had the one slit diffraction type interference, we had the two slit interferences. So we have like the one and the two slit interferences. We want to go up to the many slits. What happens as we keep adding more and more slits in? And so if we remember, the first single slit kind of gave us a diffraction pattern that went like, like this, right? And we'll say it's kind of wide, so we want this to be kind of wide out like that. And that was kind of what we had. And then we found out that the double slit interference made, and I'm only going to really look in this area here, but it made an interference pattern that went underneath that, right? And it did something like that, and it went underneath, and it stayed underneath, and went down to 0, and then went back up, and it did this kind of thing. Well, I got kind of not far off, but it went up and down like that underneath the envelope of the single slit interference. So I really want to kind of focus in on this central area here where we have just that little interference. So what we'll have happen with the double slit is we'll end up with a bunch of these peaks, right? And I'm going to put a bunch more in here. So we have a bunch of these kind of peaks inside that narrow part. Again, we're looking just in this area. And so if we add a third slit on, what happens is you get another one of these interferences, and it ends up taking and it basically shifts off a little bit from the pattern. You end up with these same maximum here in this same position. I'm going to try and draw some light lines down that we can do here so we can kind of line this up. You end up with these same maximums, but what happens is it makes them narrower, and it adds some extra little bumps in between them. So, for example, what you'll have is you'll have this come up and it'll be narrower than it was before, and then right in between you'll have another little bump, and then a narrower one, and then a little bump, and then a narrower one, and then a bump, and then a narrower one, and then a bump, and then a narrower one, something like that. And they line up. So you can still use that same equation from the double slit to find the location of these maximums. They're not going to change, but you're going to make them narrower. They won't be as wide, and you'll have these extra little bumps. So that would be 2 slits. This would be 3. When we went to 4 slits, it's going to make them even narrower, and I'm not sure I'm going to be able to draw beyond that. And then there'd be 2 bumps, and then narrower, and then 2 bumps, and then narrow. And as you keep adding more and more slits, you get this kind of continuing on in this fashion where the slits, the fringes, these bright fringes get narrower, and these guys get shorter and smaller and more numerous. And so what you end up with is just huge, just little peaks, bunches of little valleys, peak, bunches of little valleys as you have a whole bunch of slits, bunches of little valleys, and then these peaks happen in there. I didn't keep this lined up, but you get something like that. And this is called, this is basically from what's called a diffraction grating. So this is a diffraction grating. When you get to many slits, you have a lot of them, more than one, and you end up with a diffraction grating. Okay, and it ends up following an equation where we can no longer treat the small angle approximation, so you end up actually having to have sine back in it. And for the double slit, if you remember, so for double, we had d equals lambda d over s. This was our separation between our slits, and this was how far apart these split. Well, for the mini slits, this was done with some approximations. You can't have those approximations. You actually have to go through and do this without the approximations. I'm not going to go through and do that. I think it gets pretty complicated. So I'm just going to go ahead and give you for the grating, the diffraction grating, you end up with this n lambda. And I'll tell you what n is in a little bit. And actually, I think in the video I had that n up there for the order, but as you got, if n got very big, as you moved further out for these, it got really inaccurate. This stays more accurate. N lambda times d sine of theta. Okay, and this is our equation for the diffraction grating. This one you don't get in the book. You don't have that in because they really, you know, depending on your situation, you can't really go out much more than the first one. But you end up with this lambda d over s thing, and this is the version when you have a lot of gratings. N is what's called the order number. It's your which order number it is. So if you say this is the central one, which I should probably make it the tallest one, if that's your central bright fringe, it is known as the it's the 0 order. That's the 0 order fringe. And then this is the first order, that's a first order, this is a second order, that's a second order, and that's what this N stands for, and tells you which order you're looking at and how many of them you can basically have. Lambda, of course, is the wavelength. D in this equation is the slit separation, so how far apart are the slits? And that's what that is. And then theta is measured from the normal. So you know, as the light was coming in, this would be normal to the surface. Theta would be something like that. Okay. So not only can this tell you where you are, what the angle is to one of these brights, but it can even tell you how many of these you can have. All right. So maybe I should draw this a little bit sideways because that picture got a little messy. So what's going to happen is you have your little single slit, you're going to have a bright fringe in the middle, and then you're going to have these other bright fringes out here like this, right? This would be the 0, 1, 2, and the third bright one, right? So this is your bright fringe, bright fringe, bright fringe, bright fringe, and they trail off as you go out, but you get these very distinct peaks like this, and because again they're under that envelope and other envelopes and everything like that, it's interferences of interference patterns, and you end up with something like this. And anyway, you've got the 1s and the 2s like this, and theta then is going to be the angle from this normal, so from here is the angle that you get to there. So like if n was 0, this would be 0, and the sine of 0 is 0, so you'd need that. Then you'd go to the next one, and it would be n is 1, so d sine would equal lambda, and then you could find what theta was, and then n would be 2, so it would be 2 lambda, so you'd need what, you could solve what theta was, so on and so forth. But you can also use this to tell me how many of these bright fringes you're going to end up with, because if you think about it, the sine of theta, whatever number you get has to be less than or equal to 1. You're not going to get, oh, I'm writing like I'm writing in coding, sorry, less than or equal to 1. I've gotten used to programming where you do it that way. Just thinking about it, so less than or equal to 1 like that, which means that if I rearrange this, I can get that n lambda over d is equal to sine of theta, and then that means that therefore n lambda over d has to be equal, or sorry, has to be less than or equal to 1. And so you can actually go through using lambda and d and figure out what's the biggest order, what's the biggest value of n that keeps this as less than 1. So if lambda over d, so for example, like if lambda over d equaled, you know, 0.2, then the maximum n you could have would have to be 5, because that would get you to equal 1, and that's the maximum that the sine of theta can be. And in fact, I think you want to say, well, let's say it was like, if it was 0.3, then you could have n equal to 3. Let's go with that one. Let's not worry about actually hitting that edge case. It gets a little tricky there. So if lambda over d equals 0.3, then n couldn't be more than 3, because 3 times 0.3 is 0.9, and if we go up to 4, we've got 1.2, and that makes n lambda over d greater than 1, and we can't have that. And so if that's the case, you could then tell me how many of these bright fringes there are. So our maximum order that's going to happen would be 3. And so if we took this and we went out one more order, All right, let me scooch this back up. We'd go out one more order. Let's say there was another one out here for 3. Then how many fringes do you have? You have the central one, and then 3 above it and 3 below it. So that's 7 of them. You'd have 7 of these maximas. All right, and then if you want to just think about it, basically what you have is you have to have the central one, so it's 1 for the central plus 2 times whatever the order is. All right, that's going to get you how many there are, which should make sense because you have 1 for the central and then twice whatever the maximum order is. It means if your order is 3, you have 3 here and 3 here, so it's twice that. All right, hopefully hopefully that makes some sense to you, and that's going to be, I think, pretty much everything for these diffraction gratings.